Hopefully you've just had a look at how to find the roots of complex numbers. Now, one result of looking at roots of complex numbers is to take the roots of unity. So taking different roots of the number 1. Why we do this is because you'll see this interesting pattern that occurs on the Argand diagram. And there's some symmetry about the roots that are placed around that Argand diagram. So let's just take a look at taking roots of 1 step by step. So first up, we're going to start off with our number, and we'll call it a complex number with no imaginary part, z equals 1. So when we take the square root of z, we can write that as z to the half. So we're taking the square root of 1. So the square root of 1 is 1 itself. But remember, when we're taking roots of complex numbers, we need to use the polar form, right? So remember, when we started off here, this is the Cartesian form. Let's rewrite 1 in polar form. So 1 has an argument of what? Has an argument of 0. Okay, and then we're going to add multiples of 2 pi to this. So it's the same as 1 cis 0 plus 2k pi. Okay, so simply is just cis 2k pi. So what we're going to do now is we're going to take the square root, okay, of cis 2k pi, which I'm writing as raised to the half. So using de Moivre's theorem, okay, the modulus, because it's 1, it's always just going to be 1 in the front. So we're going to have cis, and it's going to be 2k pi over 2. And the two 2's will cancel each other out, so you're just left with cis k pi. Alright, so if z equals 1, then the square root of 1, this is a fancy way of writing it, and this is the polar form. We have to check different values of k. So this is a quick reminder on how to do this. So if k equals 0, we get the square root of z equals cis 0, okay? Because when k is 0, there's 0 over here. Cis 0 in Cartesian form is just 1. Great, so we just found out the square root of 1 is 1. Yep, we already knew that. Let's have a look at k equals 1. So the square root of 1, okay, we can write cis. When k equals 1, we have a single pi there. So we're going to have cis pi. Now, cis pi is 180 degrees, so that means it's on the real axis, but it's purely negative. So it's just negative 1. Awesome. Okay, so we found out the square root of 1 is plus and minus 1. We could have worked that out ourselves by using our normal methods. If I repeat this process, okay, you can also find the cube roots of 1, which you will immediately tell me 1 is also a cube root of 1. But what are the other two, right? So let's have a quick look at how to do this process one more time. So I want to find the cube root of z. So we're still using z equals 1, okay? That's my point of reference. So I write it as z to the 1/3. Okay, so I'm actually taking the cube root of cis. Okay, so we've got 2k pi raised to the 1/3. And remember, this expression came from the one above. Alright, we already worked out that 1, it can be written in polar form. I should mark that in. This is polar form as cis 2k pi. So using de Moivre's theorem, this should be cis 2k pi over 3 Okay, so that's the answer in polar form. There's actually 3 solutions here, but we can't see them, so we're going to start with our k values and figure out what they are bit by bit. So when k equals 0, I get the cube root of z equals cis 0, which is 1. As we already expected, that was one of the solutions. Then we'll look at k equals 1, so we get the cube root of z equals cis. Now when I put 1 in this, I'm going to get 2 pi on 3. Okay, 2 pi on 3 is second quadrant using angle of pi on 3. So just trying to convert this into Cartesian form. Maybe we could draw a little sketch here. Okay, so we've got 2 pi on 3 is over here. So this is pi on 3. So cos of pi on 3 is a half. Negative a half, because it's in that quadrant, and then plus root 3 onto I. Okay, lastly, when k is 2, okay, I know this is the last one because I've got a cube, so I should only expect 3 solutions. When k is 2, that'll become 4 pi on 3. Okay, 4 pi on 3 is over here, where that angle is pi on 3 there. So I'm going to get negative a half minus root 3 onto I. Alright, so I should mark in the solution on my Argand diagram clearly so you can see it properly. So let's just redraw this. So what do we have? We have 1. We have negative 1/2 plus root 3 to I. So it's kind of like, here's 1. Yep, so this part here is 1/2, negative 1/2, sorry. And this is root 3 on 2. And then we have another solution over here. In fact, if you look carefully, that third one is the conjugate of the second one. What do you notice about the solutions though? Okay, maybe if you have a look at the solution of the square root one, that might give it away. So I'll just draw this over here as well. Okay, so I should mark in this is the real, this is the imaginary. This is the real and imaginary. Okay, so the square root of 1, we had a solution at 1, and we had another solution at negative 1. Okay, that's what the cube one looks like. Now, without any working at all, okay, I'm going to extend this idea. I can immediately work out the fourth root of 1. So it's like the square root of the square root of 1. So 1's always going to be a solution, but I think you can work it out easily just by looking at the Argand diagram. So visually, there is something peculiar about where the solutions are going. Here are the answers. There's going to be 1 here at 1. I should mark in that's 1. There's going to be a solution here at I. There's going to be a solution here at negative 1. There's going to be a solution here at negative I. How did I know that so quickly? So hopefully you can see that all the roots of 1 are equally spread around the Cartesian plane, around the complex plane. Okay, so this has a separation of 180 degrees or pi. This has a separation of 2 pi on 3. This has a separation of pi on 4. Now, where did this argument come from? Have a look at the argument of the final solution, okay? So see this pi here? It says multiples of pi, k pi. Have a look at this solution here is 2 pi on 3. Well, you've got multiples, or k lots of 2 pi on 3. So without any working out, just by extending that idea, I can immediately write the fourth root of z equals cis, what do you know, 2k pi over 4, which reduces down to multiples of pi on 2, which I just realized I made a mistake, sorry. This angle here is pi on 2. Sorry, I meant to write pi on 2 here for 90 degrees. Okay? So maybe we can write a rule. Roots of unity. The roots of unity. If z equals 1, then the nth root of z, or the nth root of 1, equals cis 2k pi over n, and where all the roots are equally spread around the complex plane. Your textbook actually gets you to do some exercises that investigate this property very well. So spend some time having a look at it. More importantly, if you add the roots together, you actually get a sum of 0. And this is true for any type of root. So if you took the fifth roots, all 5 of them, when you add them all together, they will cancel each other out. I'm going to leave that for you to figure out why that works out, but I'll just finish off with one note. Notice the ones where you have complex solutions. Okay, so this is the cube root of 1 we just did before. You notice that the complex one, okay, the one that has an imaginary part, there's the other solution which is the conjugate of it. So this leads on to a special theorem. If you have a solution which is complex, the conjugate of that is also a solution as well. Okay, we'll see if we can have a look at, no, they don't have it. So if we go back to our working here, what I'm saying is, when we looked at square roots, there was no imaginary root, okay? So we don't need to do the conjugate of these. This one has an imaginary one, so that means the alternative must be -1/2 minus root 3 on 2i. This one doesn't have any imaginary roots, okay? So simply the roots are z equals 1, z equals -1, and then the other two are, oh, I beg your pardon, sorry, I did it wrong again. So this one has an imaginary one, so we've got I. So what's the conjugate of I? -I, okay? So they always come in pairs. All right, so just to double check, I can write the fifth root of z, which will be cis 2k pi over 5. So I can immediately write the solutions down. 1 is one of them. The other ones will be cis 2 pi on 5. And then I've got cis 4 pi on 5. The fourth one will be cis 6 pi on 5. Okay, and the last one will be cis 8 pi on 5. Okay, so you don't need to know what the pi on 5 is meant to be, but you can just immediately work out the solutions will be evenly spread across the complex plane. So I'd have to imagine fifths are actually 72 degrees, and the conjugates, so this one and this one are going to be conjugates of each other, and these two are conjugates of each other. Okay, so 2 pi and 5 is 72 degrees. It's approximately here. 8 pi and 5 is the same as negative 2 pi and 5. Just think about that, right? So there's another one. And then the other two are over here. Okay, if I draw it properly, this should be equally spread out. And if you join all the points together, you'll get a regular polygon. Okay, so you'll get a pentagon in this one. You get this one, you get a square. Okay, this one you get an equilateral triangle, and this one you don't get any shape. Okay, you don't get a two-sided figure. So that is the end of finding roots of complex numbers, particularly special properties for the root of 1, okay, known as the roots of unity. Please remember this property because it helps you work out the roots of 1 easily just by using the Argand diagram and using symmetry. And in an exam situation, you can quote those properties by writing it in words. You don't actually have to do the full working out like I've shown here.